Good morning, everybody. Welcome to the classroom. So today we continue from where we left last time. And last time we stopped by giving the analog of the fundamental inequality for the systems. Now we can use this to prove the existence and uniqueness theorem. I may not be doing the proof of the existence theorem explicitly. It takes it can be developed along the same lines as you did for the one-dimensional case. Now let me state the first we talk about the uniqueness. What does it say? See, you have the initial value problem here. What we want to assert is that there exists a unique solution for this initial value problem. Now we have assumed f is continuous in some region, etc., the domain of its definition, and then x naught t naught is a point in that region, and so on. And what we want to prove right now is this, that if two solutions exist, then they are identical. We are still not saying that solutions do exist. That we will take up soon. So if x1 and x2 are two solutions of the initial value problem, then x2t. I mean, it's very simple to prove, because you use this. You know that at t naught, x1 t naught and equal to x2 t naught, therefore p t naught is 0. Secondly, epsilon is 0 because both are assumed to be exact solutions of the equation. Therefore, you see that xi prime t minus f of xi t is equal to 0. That's the assumption. Therefore, you see that epsilon is equal to 0. Therefore, you see that the right hand side of this inequality is 0, which tells pt is 0. So the uniqueness is just a simple consequence of this powerful inequality. Now we look at the existence. So what we assert is that if solutions exist, then it is unique. Okay. Now we existence. So we assume these are the assumptions. F of is continuous in both the variables and satisfy Lipschitz condition x in some R. So R may be given by the following. Such that norm of x minus x naught is less than or equal to b modulus of t minus t naught for a and b, two positive constants. So we take m as the bound for okay, this is a compact region of R2 and f is continuous, therefore this is bounded. So we take m as the bound for that. Then there exists a solution of initial value problem defined on the interval t naught minus t naught plus h where h is of course minimum of a and b by n. This is exactly the same type of statement that you have. It runs on the analogous lines and you can easily check this. Now, because of the constraint that may come to understand these kind of things, it is better to first try it out for n equal to 2 or n equal to 3. n equal to 2 you can draw pictures and diagrams will give you insight into it. So that is the best way to understand these things, and that's how I do it. I mean, people may find it different, but I try to reduce it to R2 or R3 wherever it can be done, and then look at this problem. Now the important part is, again, you see that you use this kind of property. Okay, then you get a sequence of functions which approximately satisfies this, with epsilon n taken as, say, something like 1 by n, or epsilon n goes to 0 as n tends to infinity. You get a sequence of functions, and then one estimates that and shows that it's a Cauchy sequence on C, this one, C of t naught minus h to t naught plus h, and then you show that it in the sup norm it converges. So that proves the result. Now it would be worthwhile for you to put your hand on this, and at least in the case n equal to 2, you try to work out the proof of this in detail, and then of course almost word by word it can be extended to the case n. So I am not going to do the proof. Now the next type of theorem that we proved in the case is this. What was the question that we investigated? We wanted to see you have two things. See, suppose this is the region, and you have got some x naught t naught and x naught tilde so you have solutions defined on certain interval associated with x naught tilde. What you do is, it depends on the rectangle that you can draw. I mean, you are talking about local solutions, and then corresponding to this there is another rectangle on which everything works. Now what we try to prove is this: what if x naught and x naught tilde are closer to one another? Then what can you say about the solution? Is it defined on some h, for some h on the common interval? If yes, what is that? What is the sort of, I cannot say it is the largest interval on which it is defined, but locally you can at least say that there is some h for which on the interval mod t minus t naught less than or equal to h, this is defined. Okay, and that is that some estimate of that particular uh, interval, the length of the interval is given here in the next theorem. So we just make the statement, and I think you have seen the statement. This is just similar to that. Again, see, one observes this. It comes from this point. Let me explain this again. See, suppose this is x naught tilde t naught. Okay, and you have got h equal to a and b by m. So call this h and this as mh. This height as mh, this length as h of the rectangle. Now suppose you allow your x naught to vary just halfway, then what happens? See, the slope that is allowed is something like this. Therefore, the interval on which you can make assertions, the common interval on which you can make assertions, will also shrink accordingly. Okay, because if you start with some point here, then the solution can, see, in the one dimensional or one variable scenario, what you have is that you see this fxt. This talks about the direction field whose direction is whose slope is given by this number, is bound by this number. Therefore, it cannot go like this. Okay, if this is a slope, this one, then there is no place where it can grow. Once it starts growing at a lesser rate, you see that it can have only, you know, the growth is always bound by plus m and minus m. Therefore, the solution will lie inside this region. But since you start here, what happens is a solution that may not be defined on the entire interval mod t minus t naught less than h. It may come to the boundary before it reaches t naught plus h or t naught minus h on this side. So this can happen. So what we are saying is that a safe bound on which you can assert that this is true. So it is related to the distance between x naught and x naught tilde. Okay, that is what the theorem says. So it says, let me state the theorem. That is the theorem just described above. Then there exists a region S defined by mod x minus x naught tilde is less than or equal to a prime a mod t minus t naught, I think I will put b prime b a prime, which is less than a. with the following property. Namely mod x minus x naught tilde or x naught less than or equal to a prime, sorry, b prime, then there exists a solution the IVP is this x prime t equal to f of t x naught. So this, see, the extent to which x naught is away from x naught tilde, you are going to have the solution defined on a smaller interval. So nevertheless, what happens is that if this distance is strictly less than a, sorry, b, then you are going to have this defined over some interval mod x minus x naught less than or equal to h for some h. This is the statement that you have. So this is, you can talk about the error between the two exact solutions and so on, and this is a very useful thing for making such estimates. Because you see there are two terms here, one corresponding to the epsilon by k. If you are talking about exact solutions, then epsilon is going to be 0. But if your initial conditions are different, then mod px naught is going to dictate the error that you have over the interval. Okay, so you can easily use this inequality to estimate all kinds of errors. So for the details of the proof is exactly like in the the situation that we have looked at. Now the next theorem talks about the error. Yeah. Yes, please. Tell me. No, I am talking about a rectangle. I am starting with a rectangle with the center at x naught tilde t, t naught. Sorry? Yeah, I am just, I think, keeping track with what is happening in the first order case that we have looked at. Am I right? The point is how you start with. You start with this rectangle with center at x naught tilde t naught. Then how far you can vary I mean, what is the h interval that you get corresponding to the variation of the initial value? X naught minus. Yeah, in the book it is probably, I am not very sure in the book, but this is because we were using that, mod x minus x naught less than or equal to a, mod y minus y naught less than or equal to b. That's why I changed it. That's the reason. So you don't have to. It's for consistency. I did that. This is done, while writing this. In fact, just to keep that consistency. Okay, what does the next result say? See, this is to some extent boring because you are just repeating the same theorems, but for systems, because we already made the framework for working out the proof of those theorems, because we have extended the notion of the distance by replace it by a norm, etc., to serve the purpose. Next theorem. This gives some estimate of the error. Okay. Let in the previous theorem. Yeah, please. Oh. Sorry? Yeah, I'll mute it. Okay, I forgot. Right. Defined in the previous theorem. With the properties assumed. Then the solution xt of the initial value problem. The initial value problem is this, dx by xt naught x naught is continuous in the data in x naught, which means that if you bring x naught close to x naught tilde, then the two solutions will collapse one another. Okay, so or we can actually give the estimate of this x naught and t. So the solution can be written in the form x t is the independent variable, then x naught is the initial data that you give, and this initial data can be looked upon as a parameter. Now what you are asking is it continuous in this parameter? Because you see that x naught can vary, you are taking x naught to vary over some interval. So what happens when you get closer and closer to this particular what is called the base solution that you are looking at, then what it says is that as x naught tends to x naught tilde, you see that these solutions would get closer, and that's easy to estimate. So that what you are saying is that the solution is continuous with respect to the parameter. Okay, so this is what we have seen, and you have seen the technique is the following. Suppose you see this estimate, this one, if you take as your x1 minus x2 and then use that inequality, this is what you get. You get two terms. Plus the other term is 0 because you are talking about exact solutions. Therefore, this is 0. So you see that if you are working on an interval mod t minus t naught less than or equal to h prime or something like that, then you see that you can replace this by h prime. I mean h prime is less than h. Okay, so you see that this will take care of the continuity. Right. Now the next statement is, I think this is proved in the book. If you want, you can look at this proof of this, the details of this. May be worthwhile looking at it, because I'm not going to do it because it will take away a lot of time. So I'll just give the statement of the theorem. What the theorem says is the following. Okay. Suppose we make assumption that see, f is actually where these are real valued functions of the variables x and t. X is actually x1, x2, etc., xn. Now what we are assuming in the next theorem is that we assume that dfy, the partial derivative dxt at is continuous over the region, in addition to whatever assumptions that we make. Okay. If so, see, what do you get? What is the initial data? See, you have dx by dt equal to f of xt and equal to x naught, say, and this is x1 naught xn naught, let us say. So this is the definition of x naught. If so, what happens to the solution? The solution is going to be x xt x naught, and this is equal to x1 t x naught our notation was small x1 xn tx naught. These are the component functions that you have, and xi tx naught is xi t x1 naught. So if you vary the initial data, then what happens is the solutions that you get are functions of not only t but x1 naught, x2 naught, etc., xn naught. Now our assumption is this, that the partial derivative of fi's with respect to xj is continuous. If so, that particular property is inherited by the functions, the solutions xi. In fact, what you can prove is that dxi by j naught for I n exists and are continuous. So what we assert is that if you have f smooth, then there is going to be the corresponding smoothness of the solution xt if you treat this as an x naught with respect to x naught also. Okay, that means if you vary x naught slightly, then you are going to have only change slightly, and even the differentiability properties are transferred, and the continuity of the derivatives are also taken care of. Now this is the sum and substance of the next theorem, and I think you can have a look at this, and the proof I am just skipping here. Yeah, one additional result that you can prove here, which we have not done in the other case, is that suppose there are some parameters in the equation, something like, say your equation is something like this. I'll just describe what it is. You have got the equation as dx by dt suppose you have a vector mu, say something like mu1, mu2, etc., mu n also, mu m, not necessarily n, you don't need that, and t. Suppose there are some parameters here, mu1, mu2, etc., mu m and t. Now I will give an example. See, if you look at the motion of a particle, then before I state the theorem, let me explain how these things come. You see that, we have we have the equations like take the case where n is equal to 3. Okay, and x, suppose x is equal to x1, x2, x3. Then xt is the position of a particle at time t, given by, the coordinates are given by x1t, x2t, x3t. So you have x3t, and f is a vector field which depends on x1, x2, x3 and t. Now suppose you have an equation like this, then you can redefine it and get it in the form 1 upon m, something like this, and you can get this inside f and write this as g, x, t, m. So m becomes a parameter. The mass of the particle becomes a parameter. So you ask the question, how does the, suppose we change the mass of the particle, how does the path vary? Okay, this is the question that you are asking. Is a change in mass, what kind of change would result? Okay, so we are going to make some statement about the same problem, the similar problem. So what you have is this, the general scenario is this, you have dx by dt f of, this is a vector xn, some parameters mu1 m, it's not the same as n, not necessarily t. So each component of f is a function of these n variables and then these m parameters and t, like what you had here. Okay, and g xt t is 1 by m f of xt. So that is the sort of relationship that you have. So these are considered as parameters. So how do the solutions depend on these parameters? So the question is dependence of on the parameters mu1 mu. Okay, so the solution that you get would be something like this, xt, which is x then you will have this mu1 mu2 mu m coming. So it's going to be a function of these parameters also. So how do they vary with respect to the parameter? Now suppose the capital F what are the components of this? The components are F1, X1 or F5, X1, X2, etc., Xm, N, mu1, mu m. This is the given data. So if you assume F5s are continuous, not only in x1, x2, etc. xn. So it is actually an n plus m plus 1 dimensional space where fi's are defined. Now we assume fi's are not only continuous in x1, x2, etc. xn, or let us assume fi's are continuous in x1, x2, etc. xn, mu1, mu2, etc. mu1 and t. Further, you also assume fi's and their partial derivatives. So the partial derivatives are fi dxj is there, then dfi d mu j mu k. X is for each I running from 1 to n, and j running from 1 to n, k running from 1 to m are continuous. Suppose we make this assumption. What one can say? About the solution. What we can assert is that xi's which depend on t, then the initial data mu are continuous not only in all these variables but also their partial derivatives. For example, dxi by d x j naught dxi mu j mu k x's and are continuous. Okay, so the smoothness that you have on f with respect to the variables as well as the parameters is translated into the corresponding smoothness on xi's. So the systems behave very nicely in this way, which in turn tells that, see, it's all important for approximation. If you are given a field and mass and all these things, you only measure approximately in any way, however sharp an equipment you use, because there are limitations for the accuracies that you can get while in measurement of say mass or velocity or things like that. So these questions are relevant because if you make an error, how much error you will make on the outcome, so that whether what you get through your theoretical computations is something that can be relied upon. Okay, this is the reason for these kind of questions. Okay, so this is what you can prove, that is, if they are continuous and if they are also the partial derivatives of these are also continuous, then the corresponding partial derivatives of xi's with respect to t as well as x1 naught, x2 naught, etc., xn naught, mu1, mu2, mu_m, they are all continuous. This is the result that you can prove, and this particular parameters of the form mu1, mu2, etc., mu_m we did not consider in the one-dimensional case. The reason was, if you see the proof of this result, then you will see why it is happening, why it has happened. What happens is this: we are going to transform this into a new system and then solve it. So unless you prove results for a system, you cannot use it, because when we were doing the one-dimensional case, what is the analogous problem? The analogous problem is this: dy by dx equal to, or I can write this in the same language, dx by dt equal to f of t x mu. Mu is the parameter. Then if you see the proof, the way in which we develop the proof, you will immediately see that at that stage one could not have attempted it, because you needed the results related to the systems to handle this. Okay, let us see how we prove this theorem. I hope you will get the statement of the theorem from the book. See, the technique is, see, you introduce some additional equations. So you have the system of equations dxi by dt equal to fi what is our notation? I think we use this notation. Yeah, okay, x1 xn, then we had the parameters mu1 mu2 etc mu_m, for I equal to, what we do is we introduce some ad hoc equations. The ad hoc equations are, consider this also as a variable and you adjoin to this m equations j so you have now altogether how many equations? You have equations in m plus n unknowns, x1 x2 etc xn and mu1 mu2 etc mu_n. Okay, now solve these equations and then apply the previous theorem. So now you look at this as a new problem, something like dyi fyt where y has now components this is the vector, where the first n of them are x1 x2 etc xn and the next m of them are you have mu1. So you are again working on this kind of problem with the same sort of initial data that you have. So you have an analogous problem conceived in the n plus m plus 1 dimensional domain, and then you apply the previous theorem. So that will give you all the results of this. See, we did not write a theorem of this kind in the one-dimensional case, because once you incorporate this, what happens is it will be a system of two equations with the x as one variable and mu as another variable, and we had not developed the theory for the systems. Okay, so that is the remark about that. So you can have a look at this. So what it says is that the solutions, the dependence of the solutions on these parameters are also smooth, provided these functions are smoothly dependent on these parameters. Okay. So the smooth dependence on the initial data the other type of parameters that may come into the equation are transferred to the solutions also. Now I'll do one more. Okay, this is of course the extension problem. Extension problem was, we have proved the existence of the solution locally. Now we want to see the maximal interval on which the solution exists, and there of course what we have observed is that if you go to the limit of the interval on which the maximal interval, the extreme ends of the maximal interval, then two possible things can happen. Either the function x will become unbounded, or the function, the graph of the function would have, or the integral curve would have come closer to the boundary, okay, or tends towards the boundary. Now these are the two things that can happen, and you have a similar scenario here, but now you are going to a multi-dimensional domain. That's all. So we have two theorems. It's continuous. These are the conditions. It's continuous, the solution, because here you are assuming continuity on x and t, then the solution of passing through any point extended until it is unbounded, or it reaches the boundary. So extension up to the boundary of the extremal interval on which the function can be defined, the property of the solution or the integral curve is that either it reaches the boundary by that point, or the function would have become unbounded. The next theorem is about the function defined on a strip. If this is an important result for the next next stage of our problem, that is the linear problems. Suppose R is the domain T1 less than T less than T2 for some T1 T2 with X, norm of X. This is an unbounded domain, and if capital F of xt satisfies a Lipschitz condition, uniformly in every subdomain of the type T1 prime for every X, then the solution of the initial value problem for is defined on that means locally you can prove the existence and then extend it to the whole interval. So the situation is this, as we have seen, if this takes care of the entire X and this is the T interval, then this is something like T1, T2. So if X naught, T naught, some point here, or let me write here, okay, some point here, let me write here, the notation will be T naught X naught, some point here, then you see that the integral curve or the solution of the differential equation is defined on the entire interval T1 to T2. In short, if this condition of uniformity in the Lipschitz property did I not write that? So what is the condition that you have? Fxt satisfies a Lipschitz condition uniformly in every subdomain. So that's the crucial condition. Then the solution is defined on the entire interval. So if in the whole Rn plus 1 the function is Lipschitz with respect to x uniformly, then you have the solution defined on the entire interval minus t to t. Now you can see this example, dx by dt equal to x square. You see that this is not uniformly, the fxt is actually x square. So it is not uniformly Lipschitz because of, you see that this is x square. So you estimate this x1 square minus x2 square. Okay, so you get the Lipschitz constant gets unbounded as x tends to the extreme, or mod x tends to infinity. So this is the example where it fails. That is why you see that the solution curves, what happens is you see, for this problem we have seen the solution curve. So this is x and this is t. Then you see that the solution curve is something like this. It's defined from minus infinity to, and some place the asymptotes comes at, this is t naught x naught, then this point is x t naught plus 1 by x naught. This is the estimate, the extent to which it can define. It is not defined on the whole interval except one solution, that is the identically zero solution. Everything else has some interval on which it is defined. It is not defined on minus infinity to plus infinity. I think I will stop here for the time being, and then we will have a break, and I will be returning by 12 o'clock. Okay? Right. So do you have any questions, specific questions at this stage? Do you have any specific questions? Shall I close it down? Yeah, okay, fine. Yeah, Riddhi. Tell me. Hello.